Good morning, everyone. My name is Li Yan, and I'm an assistant professor in the Department of Computer Science at Iowa State University. First of all, I'd like to sincerely thank the EuroVIS organizers for inviting me to give this talk. I was originally hoped to join you in person in the UK, but unfortunately, visa-related issues make that impossible. So I'm very grateful for the opportunity to participate remotely. This invited talk accompanies a CGA impact article that I was invited to write following the 2024 IEEE VGTC Visualization Dissertation Award. My dissertation, completed at the University of Utah under the supervision of Dr. Bei Wang, was titled Merge Trees and Their Variants for Scientific Visualization. Looking back, what I found most interesting is that many seemingly different visualization problems eventually lead to the same underlying structure, merge tree. Today, I'd like to share how much trees and the related topological descriptors helped address three challenges in scientific visualization. Rather than focusing on technical details, I will emphasize the broader ideas and impact that emerged from this line of work. Scientific visualization faces many challenges, but I would like to focus on three. First, understanding features in complex scalar and vector field. Second, reducing increasingly massive simulation data without losing scientific meanings. Third, understanding uncertainty in the ensemble simulations. At a first glance, this seems unrelated. The central message of this talk is that merge tree provide a common structural representations that help address all three. A merge tree captures how connected components evolve as a scalar threshold changes. Instead of storing every data value, it summarizes the organization of features and their relationships. What makes merge tree powerful is that they are simultaneously compact and contain rich topological information. Because of this, they can serve as a common language for comparing features, feature tracking, preserving features during compression, and analyzing uncertainty. Everything I discussed today built on this idea. Let me start with data understanding. The goal here is to move from raw numerical fields to meaningful scientific features. One of the major challenges in making scientific data useful is its structure complexity. While critical points provide a compact way to summarize the underlying flow structure, the question quickly becomes which features are actually meaningful. Robustness provides a topological notion of feature significance. Intuitively, it measures how stable a feature remains under perturbations of the data. Features with high robustness are more likely to represent meaningful structures, while lower robustness features are often associated with noise. Unfortunately, classical robustness does not work well in many large-scale scientific settings. In particular, when data are analyzed through subdomains or across multiple scales, boundary effects can significantly distort robustness measurement. To address this limitation, we introduced multi-level robustness, a scalar-aware notion of feature significance that better accommodates multi-scale structures while reducing sensitivities to subdomain boundaries. The idea is simple. Instead of asking whether a feature is globally important, we evaluate its significance across multiple scales. This provides a much more reliable way to identify the structures that truly matter. And once we can reliably identify stable features, we can begin building application-specific analysis tools on top of them. One example is the tropical cyclone tracking framework shown on the right, which I will discuss next. The key takeaway is identifying the features that truly matter. Starting from thousands of candidate trajectories, which may represent tropical cyclones, topology-based stability filtering reduced the problem to only a handful of dominant features. We tested the framework on 30 years of reanalysis data. Despite using only wind speed and wind direction, it achieves performance comparable to and sometimes even better than existing tropical cyclone tracking methods with far less input data. This illustrates a recurring theme throughout the talk. Topology helps us focus on what is structurally important. The second challenge is data reduction. As simulations continue to grow in size, reducing data becomes unavoidable. But the real question is not how much data we can remove, it is how much scientific meaning we can preserve. Much of my work in this area has been driven by a simple idea. Data reduction should be feature-aware rather than purely numerical error-aware. One direction is topology-preserving lossy compression, which eventually lead to Topo-SZ. Traditional compression algorithms focus on numerical error, enforcing point-wise error control. Scientists, however, often care more about the features than individual values. This motivated Topo-SZ, a topology-preserving lossy compression framework. The key idea is to integrate topological constraints into error-bounded compression. As a result, decompressed data preserves the important topological structures that scientists rely on for downstream analysis. Another direction is dimensionality reduction. In our early work, we explored how topological information can guide low-dimensional embeddings so that important structures remain visible after projection. More recently, we have extended this idea in a new framework which is currently accepted by IEEE TVCG and already available on arXiv. Together, these efforts share the same philosophy. When reducing data, preserving scientific structure is often more important than preserving individual numerical values. Let me use Topo-SZ as a concrete example of this philosophy. The interesting result is that the cost of preserving topology is surprisingly small. The figure on the left shows that Topo-SZ consistently preserves the structure present in the original data, even under aggressive compression settings. At the same time, the figure on the right shows that its overall compression quality remains very similar to existing state-of-the-art method. So the takeaway is simple. We preserve topology without giving up much compression performance. Perhaps more importantly, the framework proved general. Several networks adopted the same philosophy and extended it to additional topological descriptors and scientific applications. This is one example of how the dissertation work evolved into a broader research direction. The third challenge is uncertainty. Scientific computing increasingly relies on ensembles rather than single simulation. Understanding structural variability becomes essential. The standard approach to ensemble analysis is averaging. Unfortunately, averaging scalar fields often destroys important structures. The figure here shows why averaging is tricky. The two ensemble members on the top each have 3 features, but when we average them, the result has 4. So, the average field is not just a simpler summary. It can actually create a structure that was not present in either input. That is why we asked another different question. Instead of averaging data values, can we average topology directly? This leads to the concept of a structure average represented by a one-center tree. The resulting framework provides both a representative topological structure and measures of structural consistency across ensemble members. This was among the first efforts towards statistical analysis and uncertain visualization for ensembles of complex topological descriptors. One application comes from neuron reconstruction. Different algorithms often produce slightly different neuron trees. Figure shown here represents a local substructure of entire neuron. Researchers need to know which regions are reliable and which are uncertain. Using the one-center tree together with consistency measures, we can directly identify regions where reconstructions disagree. The visualization immediately highlights low consistency branches and provides an interpretable representation of uncertainty. Rather than looking at dozens of reconstructions individually, scientists can reason about the ensemble structurally. One aspect that has been particularly rewarding is seeing these ideas applied across disciplines. Climate science, combustion, neuroscience, structural biology, and machine learning all appear in this slide. Although the scientific questions differ dramatically, the underlying need is the same: a compact representation of structure. Merge trees and related topological descriptors provide that common foundations. There are still many open questions. For multi-field data, we still lack mature topological descriptors and comparison matrices. For uncertainty analysis, robust structural statistics such as topological means and medians remain largely unexplored. And increasingly, we need scalable algorithms that integrate topology with machine learning and large-scale scientific computing workflows. These challenges continue to motivate my current research. Let me conclude with 3 messages. First, topology helps make scientific features understandable. Second, topology enables feature-aware data reduction that preserves scientific meanings. Third, topology provides a natural framework for understand uncertainty in ensembles. Across all 3 directions, merge trees serve as a common structural representation that connect data understanding, compression, and uncertainty analysis. Thank you so much for your attention. I will be happy to take any questions.